So we will talk about this inception, and after that, maybe after this session, we will take maybe 10 minutes break or something, and we will go to RNN, because RNN is very, very important. Yes. What? I got a question. Maybe someone was asking. Please.
Sorry, can I ask a question?
Yes, please.
For the last session, you said that if anyone can simulate the LeNet and AlexNet with MNIST data set.
Yes.
Yeah, I simulated. If you want, I can.
You have. Yes, please. So we can start with your results first. It's a good idea, Ali. So I will stop sharing, and you can share your screen.
Oh, thank you.
So. So Ali, you cannot share, right?
And not yet.
You are a co-host now.
I think now. Can you see the?
Yes, clearly.
Okay. So I use because it's like for the AlexNet, I need more RAM, so I couldn't do it on Google Colab. I use one of the TNU servers, and yeah, this is the.
Can you go step by step? Can you go step by step from the beginning, please?
Okay. I'm starting from scratch. So this is the digits that we want to find, and this is the from the data set. And in LeNet, I use a functional model API for Keras. Here you can see. I'm sorry, can you see the LeNet here, right? I'm just checking.
Yes.
Okay, that's good. So I created a functional API. I think in your the notebook that you shared, it was a sequential, but I created a functional API because I wanted to access intermediate outputs.
And yes, this is very good.
Yeah, and yeah, I use two convolutional layer and intermediate output. For intermediate output, I use a convolutional layer, but I set the number of filters to 1 to create a 2D matrix. And again, another convolutional layer and a flatten layer to flatten the matrix, and then two dense layer. This is the LeNet for my LeNet. And for calling it, I use two function. First for intermediate, and the second one is the final output. To compile the LeNet, I use categorical cross entropy. As you said, I use the same thing. Optimizer SGD, and yeah, this is the process of training the network. And the summary. If you have any question, I can stop in the summary, or I can continue. And yeah, this is the learning curves of LeNet with the validation accuracy of almost 97%. This is the confusion matrix for LeNet. And this is the intermediate output of the LeNet. Yeah, it's in this stage, it's not very informative, but you can see that the shape of the 7 or 2 is like a black dots in each matrix. It tried to shape the each matrix each digit with black dots in each matrix.
It's similar to edge detection, for example. It's
Yeah,
like edge detection. Yeah.
yeah. And for AlexNet, I tried. I used it from the your slide that you explained in the last session. I use a convolutional layer, a max pooling, again another convolutional layer, and another max pooling. And I use I think 3 layers here with the same number of output filters, a batch normalization, and activation of ReLU. Here, this is not from in the original network. I just used it here to access the intermediate output. Again, another convolutional layer, flattening it, and then dense layers. But in the end, I used 10 dense output because I want to create the digits, access the digits. So I changed it to 10. And here, because in the original AlexNet, the shape is different from the NIST dataset. So I just keep the default in AlexNet, but I use an interpolation method, and I use it from CV2 library. And this is the part that it needs 12 gigabytes of RAM. So yeah, we couldn't do it in Google Colab because it gives us like 8 gigabytes. And I resize it.
So this one to resize each image into the correct size for AlexNet.
Yeah, for AlexNet. And then I use the categorical cross entropy. I tried different learning rates, and based on different learning rates, we get to overfitting, mostly AlexNet overfit on the dataset. So I tried this learning rate, and it's working fine with a batch size of 40 and 64. I only tried 10 epochs, but each epoch took a lot of time, like 26 seconds. This is in comparison with the LeanNet, which was around 6 seconds. It's like 4 times bigger than the in computational complexity, and also in space complexity because it's bigger in size. So this is the architecture or topology of AlexNet. And this is the training.
Did you freeze? You used the whole data set for training it from scratch. You didn't use pre-trained weights.
No. I didn't use pre-trained. I used from the scratch. Yeah. If we used maybe trained models, the time would be much slower. Yeah, I agree.
Yeah.
This is the learning curves, which shows that it is not underfitted or overfitted. It's good. This is the confusion matrix. I also create a comparison between, this is the original, and these are the intermediates metrics. You see that LeanNet do some edge detection, but AlexNet try to form the digits itself. It's like constructing the image. This is the difference between LeanNet and AlexNet. And the final comparison is that the LeanNet, yeah, you can see that this is the LeanNet and AlexNet in loss and their accuracy. You can see that their accuracy is somehow similar. It's not very different, but in computational complexity, they are very different.
the number of epochs also is different.
Yeah. 10 epochs because it was sufficient. It's like it's already reached to its stable point. So I won't go any. I didn't go any further. Let me. This is the validation accuracy. It's about 97%, and for LeanIt, it was also the same. So it's both on it was 97%.
Yeah, this is very good because you trained the two models from scratch. In fact, you didn't use any pre-trained. It will be nice also if you can try to import the weights, train the weights, and freeze some layers, and to see, I mean, to make comparison. What?
Yeah, I can do that. Yeah. So and I think I request I pull request for this to your GitHub library if you want to add it. Yeah. Okay.
Yes.
Thank you. If you have any questions.
And is it easy to get access to this NTNU workstations or servers? Is it easy to run some code in those servers?
I'm sorry, I have trouble to hear.
Yeah, I mean, is it easy to get access to NTNU servers and run code and train models in?
No, because I think the servers are for each person. It's not open access for everyone to use the server. So this notebook, if you want to try the notebook for yourself, you can, like Google Colab, you can use this. I actually did it with, let me show you. In this interpolation part, you can try to like shorten the size of this test and train to like if you have insufficient memory. It's I think the error is OM. If I'm not wrong, the error is insufficient memory for TensorFlow or NumPy. I tried on both. Like I tried TensorFlow matrices and even NumPy because CV2 create NumPy matrices. Both have error with this size. So I tried NumPy, but anyhow, you can use like shorter size for the training and test if you want to use it on Google Colab.
Yes. Okay. I cannot hear you, Ali, because I just switched to another speaker. Can you hear me?
Yeah, I can hear you.
Okay, you can hear me, but I cannot hear you. So I need to use my headset again.
Okay, so I stopped sharing.
So maybe the microphone speaker. Okay.
Okay, thank you.
So thank you very much, Ali. Is it better now? I used another speaker, another microphone.
I think it's good now.
Okay, thank you very much. Yes, so thank you very much for this nice presentation and for testing those two models.
But
it would be nice also.
Yeah, I will try train AlexNet and I can share it on the GitHub.
Yes.
Yeah.
And also, I mean, how do we run any code? And because some students, maybe they don't know how to get access to the servers. How to run something in this? If you can make one slide or something or two slides and share it with me, so I can.
For what to share to server?
How to run a code. Now we know how to do it in Colab. So how to run it in another server? How it would be nice to.
For servers, I think you need access. Like you have to request it based on your project. If you need really because my project is in deep learning for frequency estimation, So you need a lot of, I need a lot of working on this area. So I have requested it. I think if your project is very time consuming and you need power and a space, computational complexity, you can request it.
HPC, high performance computing cluster.
Yeah. HPC, we in NTNU we have two different HPCs, one in general and one for IIK. But I think all the people in NTNU can use it. Can use the general. You can use it from the NTNU. Yeah.
And as you have all libraries installed, you don't need to install anything. So when you run it,
you only need SSH. Yeah, and you need to share the public key with the IT guys.
Yeah. Okay, so thank you very much, Arif, for a nice presentation. Thank you. Yeah. So I will go back to this Inception network. So I will share my screen. So can you see my screen?
Yes, I can see.
Yes. So in fact, this Inception, this Inception, it has been presented maybe for the first time in 2014 by a group of researchers at Google. And the main idea was to build a deeper neural network while improving utilization of computing resources inside the network. And this is the classical structure. To the left-hand side, this is the classical structure. And to the right-hand side, this is the Inception network or Inception modules. So in the classical way, we have inputs. We have a set of classical convolutional layers followed by maybe pooling, max pooling, or average pooling. And after that, we will have the classifier part or the classification part. In this classification part, we will have maybe number of fully connected layers. And of course, the last layer should be softmax layer for decision making or for calculating probability. Maybe in the middle here, we should have this flattened layer. So it's like an interface between convolutional layers and classifiers layers. So this is the classical structure which we know. The Inception module, on the other hand, it will be similar, but we will add some Inception modules. So maybe we can start by some convolutional layers, followed by some pooling layers, and after that it will be followed by some Inception modules and some pooling layers and so on. So now we will know what is the function of those Inception modules. So the Inception modules, it's from 2014. So today we are in 2021. So I'm sure that we should be able to see more advanced structures, and so it's like 5 years, 6 years from 2014 to date, 6-7 years. So I'm sure that there are more advanced structures. So we need to go through. We need to look around and see if there are some other modules. Maybe we need to check or study it, for example. But this Inception module, it's combination of, in this paper or in this work, it's combination of 4 layers. So the first layer, it's 1 times 1 convolution. The second one, it's, and you know this 1 times 1, what is the function of it? It's like reducer layer, for example. We use this 1 times 1 filters or convolution to try to reduce the depth of the image. So you see from the previous layer, for example, the size was 32 times 32 times 200. And when we apply this 1 times 1 convolutions, we can reduce the depth of the input volume. So we are reducing it, for example, from 200 to 64. But we keep the dimension as it is. So we keep the width and height and width as it is. We just change the depth. So the second layer, it's 3 times 3 convolutions. This is okay. And then maybe here he is using zero padding, for example, because we have the same dimension. And of course, the input is 200 and the output is 128. This number, you need to select this number, in fact. So this is user defined. 64 also here, it's user defined, correct? You need to define how many 1 times 1 convolutional filters, for example. 128, it's user defined. And after that, we have 5 times 5 convolutions. With zero padding also, we will generate the same width and height. And we will select the number of features which we need to extract, which is 32. And the last one, it will be max pooling, 3 times 3 max pooling. So in this combination, it will generate the same. And of course, also, it's a 3 times 3 max pooling. From this one, we will get 32 feature maps. And after that, we will have this concatenation. And in this concatenation, we will combine all those outputs from each layer. We will combine them together to create one output volume. So in this case, if you sum 64 plus 128 plus 32 plus 32, we should get 256, right? So it's just concatenation. So the outputs of those layers are concatenated into a single output volume, forming the input of the next stage. So now we are preparing the input for the next stage. So you can concatenate the depth of the 4 outputs to create one output volume of dimension 32 times 32 times 256. I mean, the output from each layer, it will be the same size. So it's very important. If we will concatenate into a single volume, it should be, it must be, or it should be important to have the same dimension, right? All feature maps generated from those layers should have the same width and depth, width and height. So this 1 times 1 convolutional layers, the idea here is to add this layer before bigger kernels, like 3 times 3 and 5 times 5, for example, to reduce the depths, which in turn will reduce the number. So we add it, in fact, before. So if we need to apply 3 times 3 or 5 times 5 filters on an input volume, it's smart to apply first 1 times 1 convolutional layer, because this 1 times 1 convolutional layer, it will reduce the depth. And then when we reduce the depth, we will reduce number of calculations or number of activations, which the next layer will do. So it's just a way to reduce, it's like dimensionality reduction or reducer layer, where we try to simplify, try to reduce amount of calculations or amount of activations. So for example, I have some input volume, and this input volume, it's 32 times 32 times 200. So you can see that the dimension, height and width, it's 32 times 32 pixels. But the depth here, it's 200. And if you want to apply 5 times 5 filters to this one, how many operations we want to do, in fact. So if we will apply this one to the input volume directly without the bottleneck, without this 1 times 1 filters, we need this number of operations. We need 163 million operations. So you can just imagine how much calculation time we need to make all those calculations. But if you will use this bottleneck layer or the reducer layer between applying this 5 times 5 filters, we will be able to reduce the number of computational number of operations into 16.3 millions. So it's like reducing it by 90%. So this is very, very efficient. So adding those bottleneck or reducer layer or dimensionality reduction layer, for example, if you can call it dimensionality reduction layer, we will try to reduce number of operations or number of calculations or number of activations. So we will make our model faster, train faster. So the computational cost, when you are calculating the computational cost, you can just, in terms of operations, for example, multiplications, activation, and so on. So the idea of this convolutional layer is to preserve special dimensions, which is height and width. So we try to keep the special dimensions, which is height and width of the input volume, but change number of channels of the volume. We try to change number of volume or the depth. When implementing it in moderation, you can shrink representation size significantly without hurting performance and save a lot of computational cost. So this is very, very smart to use 1 times 1 filter. So even now, you can try to really I mean, you have some computational resources, very good computational resources. So maybe you need to try to come up with new model, right? Because we know that, I mean, start building a model, start to build the backbone of a model, and start trying to maybe simplify it. So I suggest, for example, you can start with a model for for classifying a data set or whatever. And after that, try to improve the maybe the performance by adding those 1 to times 1 convolutional layers, maybe inception layers. We can add also some inception layers. Maybe you can come back with a model similar to the one which has been developed by Google, which is the inception model. So the inception module with dimensionality reduction. So we have the basic model. We have only here the dimensionality reduction layers here. This 1 times 1 convnet. This one 3 times 3. It consists. Its inception module consists of 4 layers. You can add also. You can add those 1 times 1 convolutions before each 3 times 3 convolutions to try to make it simple. Try to make it simple, more simplified. So you can just add this one here, for example. So in this case, we will be sure that we will try to control the depth and try to simplify the model. So it will in fact adding those 1-to-1 convolutions here. It will try to reduce number of computational operations, which each 3 times 3 and 5 times 3 convolutions will do, for example, and it will make it more simple. And it's the same also for the max pooling. We will make it simple for the next layer. And we will do at the end, we will do depth concatenation. So this is Google Net, in fact, Google Net. So we start by input. We have here 7 times 7 convolutions, followed by 3 times 3 max pooling, followed by 1 times 1 convolution, followed by 3 times 3 convolutional, and after that followed by max pooling. So this part A, it's identical to AlexNet and LeNet, which contains a series of convolutional and max pooling layers. This part, it's identical, in fact, to AlexNet and LeNet, this one. So in fact, you can say that maybe GoogleNet, it's based on the backbone of AlexNet and LeNet. It's the same, but here they made these modifications by adding those inception modules. So the first part, it's identical to AlexNet and LeNet, and after that we will have this one inception. It's followed by 3 inception modules, followed by each followed by 3 times 3 max pooling layers. So first you will have this inception module, right? Followed by max pooling, inception module, followed by max pooling, followed by inception module, followed by max pooling. It's called the global average pooling, for example. And after that, we will go to part C, which is the classifier part, which is the fully connected layers. So you can just say that this GoogleNet, it's identical to AlexNet and LeNet, except adding those inception modules. So in fact, we should be able. I mean, we really need to motivate ourselves to try to develop new architecture based on one of those. Maybe combining AlexNet and LeNet, for example, and adding those. I mean, just imagine, you can just try to imagine a way for building a new structure and testing this new structure and compare it to it could be a publication, compare it to AlexNet, LeNet, GoogleNet, for example, in terms of performance, number of computation, accuracy, all those numbers. So if we can improve those numbers, maybe our architecture can be famous and it can be used by other people in the future. So, but this structure, it's a simple structure, and this simple structure, it's based on the backbone of AlexNet and LeNet. So the first part, it's identical, it's the same, and after that we will follow it by 3 inception modules, and each inception module will be followed by max pooling layer, and after that we will have part C, which is a classifier, which is standard. So in this standard part, we will have one fully connected layer followed by softmax layer, and that is it. So I did, in fact, when Ali has been trained his models, he built the model from scratch. He built the whole structure as it is, and he retrained the model from scratch, which is really very good. But as also, I mean, you can do it, or you can try to import trained weights, maybe from. I mean, you can import the trained weights, and you can freeze that part, and you can train only maybe the fully connected layers. Maybe this part, this is the most. I mean, this is a transfer learning, so you can import the whole model, pre-trained model, especially this convolutional part. This is the most computationally expensive part. So that part, we can import that part, and we can freeze all those weights because we don't want to, we don't want to retrain the model one more time. And after that, we will make some modifications here in that part, in the decision-making part or the classification layers, and we can only train that part and apply it to our own application. So this is a transfer learning. But Ali, this morning, he trained the model from scratch using the data set which he has. And I was very happy because I was expecting that maybe his model will overfit the data because the data set maybe it's very small. But he was lucky that it was not overfitting. So, but I hope that he can maybe try to use also pre-trained weights and try to make comparison. Is there any comparison in terms of time and performance and so on? Yes. CFAR 10. CFAR 10, it's similar to MNIST, but it's 10 classes. Those CFAR 10, in fact, it's images for 10 objects. And you can see some objects here, for example, trucks, cars, animals, or horses, boats. So there are 10 classes. And we need to use this inceptive or inception model for classifying this example. This one, it's identical to, it's exactly the same as MNIST, but MNIST, it's a grayscale images. So each image is one channel, but in CFAR 10, each image it's RGB, which is 3 channels. So because Inception, they made Inception for RGB images. So if you want to use MNIST here, you need to convert MNIST from grayscale into RGB. So you need to have this transformation. You need to transform it from grayscale into RGB, and also resize, because for each model, for each pre-trained model, the input shape is important. So they provide, with each model, you will see that, okay, this is the input size which is accepted here. So the minimum size which is accepted by Inception, in fact, it's 57 times 57 times 3. So each image must be at least 75 pixels width, 75 width height, and 3 channels, which is RGB image. So I just imported this Inception version 3, and I used the weights from ImageNet. So it's a pre-trained. So I used the weights which has been trained on ImageNet. I mean, in case of Ali this morning, he built the model from scratch. In fact, it's the same model, but he initialized the weights with random values, and he trained the model from scratch. But he can import the weights from weights which has been trained on ImageNet, for example. So in this case, I will use the convolutional block which has been trained before. So include top equal false, which means I don't need to include the top layer, which is the fully connected layers. So include top equal false. I imported this model, but I imported only the convolutional part. So I'm not interested in the decision-making part or the classification part. So this is the top part. The top part here, this is the fully connected layer and softmax. No, I don't want to get that one. I want to build this one for my application. So in this case, if you want to exclude the top part, you need to write here include top equal false, which means we will not include the top layers, which are responsible for classification. And you need to define the input shape. And after that, I will flatten. So I just imported it in one line. I mean, if you can see, when Ali he built his model, he imported the whole model. He built the whole model from scratch. So it looks like larger because he imported it from scratch. He can do the same here. In fact, he can import also the Inception in the same way, but he will not freeze it. So it will be retrained. So, but anyway, we will flatten after this Inception. So when we imported this Inception version 3, I imported that part, in fact, this part. I imported that part. And this part, to connect it was fully connected, I need to flatten the output feature map or the output volume. So we need to use here flatten, because this flatten, it will flatten the output volume from the convolutional part to be prepared for the dense layers. And after that, I used one dense layer, which has 1024 units. Activation is RALU, followed by dropouts followed by another dense layer with 128 units. Activation is RELU, and finally followed by soft max layer with 10 units. 10 units because CFAR10 has 10 classes. So you have an image, and each image should be classified into one of those 10 classes. So this is the model. So it looks very compact, but if you want to make it similar to Ali, it will be the same. You can build all layers, layer by layer. You can build it step by step, and after that, initialize all weights with random values, and train the model using the data set which you have. But maybe the model will overfit because any data which you will have will not be comparable to ImageNet. ImageNet, it's very huge, right? And each image data, it's RGB images. So when we try to extract feature maps from this data set, it should be comparable to any kind of machine vision applications which we are doing today, for example. So the most important here, if you can count layers, so I imported here inception module as one layer. So this one, it's in one line. When it's in one line, in fact, it's like one layer. So this is layer number 0, and the flatten will be layer number 1. So if you can look into here, this one. So in this inception, this is layer number 1, layer 0, sorry, or layer 1. You can just call it layer 1, or I will call it layer 0 because it's layer 0. So it's layer number 0. Flatten, it will be layer number 1. This dense layer, it will be layer number 2. This one, it will be a dropout, it will be layer number 3. This one, it will be layer number 4. This one, which is a soft max layer, it will be layer number 5. So if you can see here, we imported inception module as one layer. So this is one layer. If you want to train this model, it's fine. You can train it. If you have enough data set, you can just train this one fully. But if you want to freeze this one, we need to write this one, model dot layer 0 dot trainable equal false, which means I will train the whole model now, but I will exclude layer number 0, which is the inception module. Right? So now we are freezing this layer. We don't want to retrain that part because this part, it will take a huge time, and it needs data, in fact, because this is how many weights here do you see? 21 million. It's around 22 million weights. So the number of weights, number of parameters, number of those parameters are weights and bias, right? Those parameters are weights and bias. So the number of parameters here in the layer 0, which is the inception module or the inception part, it's a 21 million weights. So it's a huge number. So if you want to, if you want to adjust this huge number of parameters, it's okay, but you will need computational resources, and also you will need big data sets. Otherwise, the model will overfit your data set quickly. So maybe if you are using CFAR10 for training this one, maybe Ali can test it, for example, train this model from scratch next time, and make comparison with this one, for example. Maybe it will overfit. We don't know. So we will freeze that part, which means this huge number of parameters we will keep it as it is, right? It will be intact. We will not touch it. We will keep it as it is. And a number of layers in the dense, this number, how can we get this number? This number, it will be, in fact, 1024 multiplied by a number of inputs, which is this number after flatten, or this number. It will be this number multiplied by this number plus this number. Can you check it?
It's correct.
It's correct. Okay, because after flatten, those will be the number of pixels or number of inputs to the fully connected layer. So if you want to calculate number of weights here, it will be this number multiplied by this one plus bias, which is 1024. We will have dropout. Dropout does not have any parameters, and after that it will be followed by a dense layer. This dense layer will have 128 weights. So total number of parameters here will be 128 multiplied by 1024 plus 128 to get this number. And the last layer, which will be the soft max layer, it has 10 outputs. So the number of parameters here will be 10 times 128 plus 10 to get this number. So this is our model. So I didn't put the code here also, but also we will use categorical cross entropy, as Ali mentioned this morning, and we will train the model. And after training, this is a training and validation loss. This is training and validation loss. So for training, it goes down, and for validation, it was going down. Do you see? It was going down, and after that, it goes up, right? Which means the validation error increases, right? Which means maybe the model is overfit. It's an indication of overfit, correct? Because I mean, as you can see here, we used the 50 epoch, but from here, we didn't use early stopping. Maybe it's a smart also to use early stopping, because maybe we don't need to continue until epoch number 50, because the model is overfitting. It looks overfitting. How can we discover it? We discover it from the validation loss. So training loss, it will go down all time. So if you keep training your model, this one will go down all time. So we don't care about that part, in fact, because this one, when you train your model, it's logic that this one will go down all time. When you keep training, the training loss will go down all time. But the problem, we need to keep an eye on the validation loss. This is very important. And if you can see here, the validation loss here with some value, and it was decreasing maybe for 6-7 epoch, and after that it started to increase. So in fact here at that point here, the model is started to overfit. Correct? Can you see it? Because this one was going down, and after that it started to go up, which means the model overfit my dataset. So even we used here transfer learning, we frozen layer number 0, which is the inception module, but also maybe this number of weights is still too high for our model. So maybe we used here, how can we fix it? We used here drop out after the first dense layer. Maybe we need to remove one dense layer. Maybe 2 is enough, not 3. Now we have 3 fully connected layers. Maybe we need to reduce the capacity of that part, because that part overfit quickly. So maybe it's a smart to maybe reduce, just to keep 2 dense layers. Use drop out. Use also maybe early stopping. Maybe the dataset is small, so maybe it's a smart to use some data augmentation, for example, right? Data augmentation, where we can try to increase the size of the dataset. Data augmentation. So we play with the images to try to expand or extend the size of my dataset. Yes. So this is the inception part. So the idea here, in fact, it's to not to use the inception part, but try to create new architecture. If you can create a new architecture, maybe this architecture will be very, very successful, and it will be used and it will be cited everywhere and so on. So in fact, we really need to think, how can we think and try to come back with new architecture, which is maybe, but I mean, there should be a logic behind it. So if we will develop something different than Google Net, for example, we need to prove why. Is it performance is much better? Is it more accurate? Is it less computationally expensive, and so on? So we need to find some excuses, or we need to give reasons. Yes. So any question for this inception module?
I have one.
Yes.
Where does the name come from?
Inception?
Yeah.
Oh, this is a good question.
I mean, is it just random, or does it have anything to do with the structure?
No, we can. I can Google it. In fact, what is the meaning of inception? Yes. Again, it's the meaning of beginning of an organization or something, start up or something. So maybe in fact there is a movie called Inception, I guess.
Yeah, that's why I asked if there is any connection to that.
Yeah, it's like establishment of starting point of something. So like so Inception, it's like starting or starting point, or because maybe like at some point in the structure we reset and we have start up each point maybe, and yes. Yes, so if we can go to the so any other questions, I will search for the reason for calling it Inception, and I will come back to you in why. Yes, so the last one, it's ResNet, and it's a residual neural network. It's a ResNet. It came from Residual neural network, and it was developed in 2015 by a group from Microsoft research team. So GoogleNet, it was 2014. ResNet, it was 2015 by Microsoft. And they introduced this novel residual module architecture with escape connection. So they introduced here something called the escape connection. So I mean the development here, it's escape connection. And escape connections are shortcuts that allow the gradient to be directly back propagated from earlier layers to later layers, creating a shortcut path for the gradient to flow through, solving vanishing gradients. A way to overcome this vanishing gradient problem. You know, when we have a model and this model cannot train, it's because vanishing gradient problem, right? So this shortcut connection, it will provide a different path for the gradient to flow from later layers to early layers, or from early layers to later layers, creating a shortcut or short path for the gradient to flow and to solve the vanishing gradient problem. Another important benefit of the escape connection is that they allow the model to learn an identity function, which ensure that the layer will perform at least as well as the previous layer. It's like providing information and supporting information to the next layers. So we are sure that they will be able to learn at a performance at least equivalent to the previous layers, right? Do you know? So we will go through it first. So this is a traditional network architecture. We have two layers or number of layers or a stack of layers connected together from left to right. I mean, all time we are going from left to right in CNN, for example. So we have some layers, and those some layers will make some processing or representation, and the output from those layers we will feed it to the next layer. So we will go from left to right. And the other one, it's with escape connection. So in this case, as you can see here, in the traditional way or the classical approach, the input to one layer, it will come from the previous layer. So the performance of this layer, of those later layers, in fact, it will be based also, it will be dependent on the performance of the previous layers or the input volumes which is coming from those layers. So the idea here using escape connection, try to provide more information to the later layers using this kind of shortcut. So it will not only process the data coming from previous layer, but also you will provide also maybe like raw data or more fresh information from previous layers using escape connection. And of course, we will have some concatenation here as well. So we will have some, we will have the output volume coming from one layer. You need to concatenate it with the information coming through this escape connection. So escape connection plus the main path. So in traditional network, convolutional layers are stacked one after the other. In ResNet, we still stack convolutional layers as before, but we also add the original input to the output of the convolutional block. So you will have here a block So imagine that we have some input data, we have some input volume here. This is the original data. We will process it. So after some block of convolutional layers, we will have a convolutional layer, maybe followed by some, maybe by maybe followed by some max pooling layers, whatever, and another convolutional. So anyway, we will have this one. This is convolutional block. We will have a block of convolutional. So when we feed it with the original data set, we will get some feature maps here, right? So this feature maps should be introduced to the next layer. So we will have here another convolutional layer maybe, or we will apply the maybe we will apply the activation function directly to those numbers. So the idea here is to add the original input to the output from those convolutional layers here. So we will add also, we will add the new representation of input volume plus the original input volume one more time here, and feeding this one to the activation function. So the output here, it will be applying this activation function to the outputs which are coming from the convolutional block plus the original inputs. So this is the idea. So if you want to write like pseudocode for it, so for example, the shortcut here, we need to store the input. I mean, we have the inputs. For example, imagine that we have convolutional layer. It has some filters, number of filters, filter size, for example, whatever. So the input to this layer, we have this convolutional layer. The input to this layer is X. And we will process it, and we will get new representation. We will call it X. After that, we will apply this X to the activation function RELU, for example. So we will apply this X here to this RELU, to the activation, and we will get some values. We will apply those values or this volume to a new convolutional layer one more time with the same kernel size, maybe with the same number of filters or different number of filters. So we will get X here. So this one, it's the new representation after the convolutional block. So this X now, it's not the input, but this is the new representation of the data, or the feature maps. This is the feature maps. So it's important if you need to use this short path, for example, or skip connection, we need to store the input volume. We need to store it in somewhere, so we can store it in X shortcut. So just to store it before processing it, we need to store this one here. So X shortcut equal X. It's just a way to store the values for next. I mean to feed it to the next layer. So now I have the original. So this one, it is the original input. This one, it is the original. We just stored it before processing. And after applying this convolutional block, we will get new representation or new feature maps called X. Now we need to add them together. So we will add X and X shortcut. It's like concatenation, maybe like concatenation. And after that, we will apply this volume to the new activation function, to RELU activation function, for example. So you can say that the convolutional block here, it's conv plus RELU plus conv, and after that we will add the original input to the new representation. So here we will have X plus X shortcut, and after that we will apply this one to the RELU, to the new activation, to get the output here. So this is the maybe skip connection block. It will be like this. So now we understand this block. So now we need to know the building blocks of residual neural network. So ResNet, in fact, it's composed of a series of these residual block building blocks that are stacked on top of each other. So this is the classical CNN. We will look into this classical one. So this is the classical CNN structure or architecture. So we have some inputs. Those inputs, we will feed it to some convolutional layers followed by max pooling layers. And we will repeat this process several times. And after that, we will flatten the output here. At that point, we will flatten the output here. And then we will feed the output to the fully connected layers and softmax layer. So this is a traditional way for doing it. In the inception, it's exactly the same, no problem. But we will start by convolutional, followed by max pooling. And after that, we will have some inception modules. And each inception module will be followed by max pooling as well. So this is the inception modules, which has been developed by Google. the ResNet, which has been developed by Microsoft, it's the same. Also, the first part will be the same. Do you see? The first block will be almost the same. So we will have these convolutional layers followed by max pooling, and after that it will be followed by a number of residual blocks. And at the end, it will be, we will use max pooling, and after that we will use here flatten, and after that we will provide those inputs to the fully connected layers. So this is a comparison between classical CNN architecture, Inception, and residual ResNet. What is the residual block? This residual block, it will be different from model to another model, in fact. So in ResNet, it has the same structure, but you can also try to mix, try to think, is it possible to combine inception modules and residual blocks? Is it possible? You just need to match parameters together. Because when we concatenate, we need to have this concatenation done correctly. So you need to be careful about the size, right? The size of each image, height and width. This is very, very important. Special dimension of each feature maps. So the what is the residual block? So the residual block here, we will have the original input to this block. For example, we will apply convnet, batch normalization, activation, conv, batch normalization, residual, activation, conv, batch normalization. So it will be like this one. So also those modules, in fact, are identical. In fact, those modules are identical. And after that, we will have the feature map or new representation here as the output. We will concatenate it with the original input. So we need to store this one. We can just call it shortcut X or X shortcut equal X. And we will sum it with the output from this batch normalization here. And we will apply RELU, because we are supposed to apply here RELU, right? If you look into this block, it's conv followed by batch normalization RELU. This one, it's exactly the same. It's conv followed by batch normalization RELU. This one also, it should be the same. Conv, batch normalization RELU activation. But before feeding the output to RELU, as we do normally, we will add to it the original inputs, right? And how can we do it? So if the size here will be the same, it will be pixel-wise. It could be pixel by pixel, right? So if the input volume here if the output representation here has the same width and height as the input volume, you can just add it pixel by pixel, right? So it will be pixel-wise something. So adding it pixel by pixel, and you will send this one to the RELU, right? There is this ResNet 50 in Keras. It's 50 layers. In fact, it consists of 50 layers. And yes, it consists of 50 layers. So it consists of number of convolutional layers and the number of residual blocks. Please, you can Google it, because maybe the space, it's not possible to have it here. But you can just check the structure of ResNet 50. But here also I will do it as we did before with GoogleNet. I will do it exactly the same. So I will import ResNet 50 as one layer. I will import it into my sequential API as one layer. So it will be layer number 0, this one. So I imported it as one layer. Weights are imported or trained using ImageNet. Include top equal false, because I don't want to include the top one, because the top one is based on my application. So maybe the ResNet was used for different applications. It has been trained here for ImageNet. And as you know, ImageNet, we have 1,000 classes. You remember? So the top part will be different. Here, I want to use it, for example, with CFAR10. And in case of CFAR10, we have only 10 classes. So I need to modify that part. So this is the reason for not including the top part. I don't want to include the top part because I want to use the advantage of ResNet in feature extraction. This is the most important for me. And after that, I will flatten the output from this ResNet. I will flatten the output from here because I didn't include the top part. I didn't include it because I don't want it. Because for ImageNet, If I will use the full ResNet, which has been trained using ImageNet, we will have 1,000 classes. But in my CFAR10 here, we have only 10 classes. So we need to modify the top part. This top part, it will be fully connected layer, followed by softmax layer. So it will be like this one. This is the input shape. It will be 32 times 32 times 3. So it's RGB image, which means if CFAR10 is not in the same size, I need to resize it. Correct? As Ali did today, he was resizing. And he said that that part was very computationally expensive, and we cannot use it in Colab, and he has to do it in the server because it requires big memory. So the input shape will be 32 pixel times 32 times 3 because it's RGB image. The output from this ResNet, it will be flat in here, and after that I will add also the 3. It's just copy and paste from the other one. I just imported ResNet instead of GoogleNet or LeNet or whatever, or Inception, right? So I just changed this one into ResNet. So it will be followed by this dense layer, followed by dropout, dense layer. This one is softmax layer. So number of outputs will be 10. And just remember this one. If you don't want to retrain the model, you need to add that part here. Model.layers 0 .trainable equal false, which means I don't want to retrain the models, the weights of my ResNet. I will just use it as it is from ImageNet. We will not play with it, right? Because if you try to train it, you will just destroy it. So you need to have enough data comparable to ImageNet if you want to retrain it from scratch. So chances to overfit will be also very high if you, at the moment, using Inception and using ResNet, we can see the model overfit. So can you just imagine what will happen if we try to adjust the parameters of this model? I don't know how many parameters. Yes, number of parameters in this in ResNet. It's 23,587,712 parameters. So it's 23 million parameters. Compared to Inception was 21. So it's more, in fact, it's more parameters. So the Inception model, it was 21 million, but here it's 23 million. 23 million weights and bias. So this one will be the same number. I mean, the output from here, it will be 2048 pixel values. So this is the number of parameters of this dense layer. This is the number of weights. So if you can look into here, this is the total number of parameters of my model now. So it will be 25 million weights and bias. Number of trainable parameters, it will be 2 million. And non-trainable parameters, it will be 23.587,718. So this number of non-trainable parameters will be the number of ResNet parameters because we frozen that part, right? We frozen that part. So that part will not be trained. So this number has been calculated here as non-trainable. So we will not train this one. We will train only the models of the fully connected layers, dense layers, and softmax layer. Only the last part is the classification part, not the conv part. Here also, as you can see here, this is the training and validation loss. I mean, don't worry. I mean, don't look into the training loss unless your model is underfitting. So this one will go down all time. This one will go down all time. No doubt about this, because this is a loss in training. If you will keep training your model, this part will go down until it's close to 0 maybe, right? So this one will go down all time. So the problem here, which we need to take care of, is the validation loss. We start the validation loss from some point here, and it goes down, which is very good. Do you see? Until maybe epoch number 10. It was better to stop at 10. Because I'm sure that the performance here was much better. I mean, the performance here after 10 epoch was much better. So if we are using early stopping, maybe the model will stop at epoch number 10, right? But because we didn't stop and I continue training the model, So the model starts to develop overfitting. I mean, overfitting has been developed, and now it's, I mean, we can see it because, I mean, the validation loss keep increasing all time. It will keep increasing, which means my model cannot generalize. My model just memorized the training data set, and it cannot generalize, and it cannot classify the validation set, because this error will keep increasing all time. So the performance was much better here. So it was better to stop here at 10, not continue until 50, because, I mean, there is no reason for doing this, because my model, the performance is much worse, right? It means you train a model. I mean, you know the overfitting. What does overfitting mean? So this overfitting, it's a very dangerous problem. Underfitting is much better problem. We can solve it by making the model more complex. How can we solve this problem now? We need to go to the structure of my model here. Maybe, I mean, this model, this conv part, we cannot do anything here. So maybe you need to simplify this part. Maybe 3 layers are too much, right? So maybe 2 layers will be enough. And also try to reduce, maybe we need to delete this layer, right? Because this layer alone, it generated more than 2 million weights. 2 million weights. So maybe we don't need to have this one. So just try to remove this layer and try to retrain the model one more time and check the performance. I'm sure that the performance will be much better, because when we remove this layer, we will reduce the model capacity. So the model will do more effort, in fact. Do you know, it's like you have a person who is very strong, is bodybuilding, and you just give him very small weight to train and to just to go for a competition. It's nothing for him. I mean, it's much better to give him enough load, for example, or try to select one with less capacity. So how can we fix this one? Maybe by removing this model, this layer, which generates more than alone, it generates more than 2 million weights. So if we can remove this one, maybe the performance will be much better in terms of overfitting. And this is the confusion matrix. Yes. So in fact, we finished this, I mean, number of slides, but as you can see here, we can, it's until 2015. I don't know. I'm sure that after 2015, there are more models. And in fact, your role now, maybe you need to try to develop your own model. Try to develop a model which people will be citing for 5 years or 6 years in the future. Try to make combination between those models together and build your own model architecture. We know all those models. We can study it more, and we can know advantage, disadvantage of each one. So we can make some integration between 2 models and try to make something, I mean, maybe more accurate, maybe less computationally demanding, and so on. We have some questions. Yes, transfer learning for, I need to ask you concept. Yes. So Amir, he was answering the question for inception. Amir, you can talk, please. Amir, are you with us?
Hello, I'm Brahani, not Amir. I think I shared the link, and you can see that the name Inception comes from the movie itself. So, so if you open the link, you can see how the name Inception comes from.
Okay.
Yeah.
Yes. So thank you very much, Brahani. Yes.
Yeah.
Oh, okay. We need to go deeper. Okay, I will look into it after the class.
Yeah.
Yes. But also, Omer, he was answering also. He wrote that Inception layer's name is based on the concept that combines many conv layers. Yes, Omer, can you say something?
Yeah. This is basically thanks. He also shared a link from a movie. No, we need to go deeper, but anyhow, yeah.
Yeah, because we go deeper by combining, by concatenation in deep.
So basically, it concatenates, it combines, it connects several convolutional layers. So so that's why the authors of this model gave the name inception layer to because it is basically a combination of different architectures in an inception layer. So that's why they gave this name to the layer. And whenever, as you mentioned, that we need to build our own model. So whenever you are building your own model, it's your authority. You can name it whatever you want. So there's no science behind giving the specifically the inception, but you can name it inception because it basically it basically combines the different layers. So you can name it. You either if you are building, you can name combine the layer. So no problem.
But Omer, what about the idea of combining different things and try to come up with new architecture, which is
sorry, combining?
I mean, creating a new. We are here, for example, in Norway. We are here at NTNU. Is there any chances that people should work together and try to maybe develop new architecture which can be used and similar to those? Because I feel that people in US maybe they are 10 years ahead. And
yeah. So for this concept, for example, I would go with the example of VGG network, which was developed by at Oxford University by a geometric group of Oxford. So they developed 16-layer and 19 layers architecture, which is VGG 16 and 19. So for that, there is basically a team working on developing such models, and with this ResNet 50 or 105. So basically, there are teams which have very big data sets, and it's not only one person. Maybe in rare chances it can be one, but it basically the teams that can develop such models. So if you want to build your own one, for example, during my master's thesis, I worked on combining asymmetric learning based hashing with the generative adversarial network with a GAN. So I named that network, that model AGAN, AGAN, and that will be published very soon in a journal. So basically what we want to do is first we need to understand the architecture, and then if you wanna do to build your own network by yourself, then just combine different architectures, and if you can do it, you will probably come up with a new model.
So but of course we need to compare it with original models and to prove that it has something different. It offers maybe better accuracy, less time for
so that is basically the validation. You need to validate on several with several parameters and on different and several data sets, and then you can check the validation and accuracy of your model. So I think we can build a model, but we need to work in a team. This is for all.
Yes, thank you very much, Amir. We have also Tariqo. He said that transfer learning for using pre-trained models. I was able to find other models from Keras applications, but not AlexNet. Is there other way for finding weights of AlexNet? I guess AlexNet. How can we get AlexNet weights? Anyone has any answer?
I think we could find it in GitHub because there is no library.
It's not in Keras. You need to import it from GitHub. Yes, this is correct.
But if you use TensorFlow 2, you can find it on GitHub, and if you use TensorFlow 1, you can download it on the website of AlexNet because it is implemented in TensorFlow 1.
Okay. So thank you very much, Ali.
I can share the links.
Okay. Yes.
Yeah.
So any other questions for this part? So thank you very much. So we will take maybe 10 minutes break, and we will start again at 10:20 with 10:30. We will start again at 10:30 with recurrent neural network. It will be introduction today, and we will continue until end of April. Yes. Thank you very much.